It's our pleasure to invite Dr. LaRue to give his talk about neural network. And Dr. LaRue, can you first introduce a little bit about yourself and then give a talk? And it's all yours.
Okay, James LaRue, you see my name here. There's an email if you want to contact me. It's stuff I've been doing for a bunch of reasons, which you'll see. Neural networks, both real and imaginary. So let me just move this right here. Okay, so my background is definitely a technician, as you can see here. All right, hands-on electronics, component level. So my wife, she flustered me enough. I went and got my PhD. I was doing matrix methods, and the way I even look at a matrix, I look at the component level, pixel by pixel, just like I do over here. And then in that, I learned things called, the singular value decomposition, the independent component analysis, that kind of composition. So I learned all this stuff. So that's my background. Out of college, work in commercial, in other companies, and that's what I do. All right. So let me go here. Okay, so that's the overall thing. That be my next talk this spring. If I'll get together for Helen there, is connecting the real and I call the imaginary. So today I pretty much focus on the part one is going to be the imaginary. I call that because it's the artificial neural network. Okay, so but you'll see at the very end I'm going to start tying in DNA. Anyway, let's go to it. So that's what I'm going to start doing. The overview, it's a joint analog digital communication signaling. So I will be taking the EEGs. So I will show you how I form my EEGs now. I don't do it the normal way. And then with the artificial. So I'm going to give you a left eye, right eye example. What you see are arrows. Okay, if I look at the left eye, those are the neural network from V1 to V6, and the right eye, another neural network, artificial. But what you see the arrows going back and forth because you learn you can form bi-directional associations. I mean, there's a little trade-off, but I'll show you what I mean. But you can actually go across too. So let me that's the overview, okay? All right, so part one, we're going to start with the artificial imaginary convolutional neural networks. They're going to bring in the broad and how I resonate associations to skip the interoperations. Again, there's a trade-off, but it works. Okay, and then in the context of a real neural network, our brains, electroencephalogram, I'm going to show you how I developed a striatal beat frequency approach. Both these approaches are patented, by the way. Okay, because I don't want anyone else I don't mind if people take it, but they're not going to keep me from working on this. And then anyway, and yeah, the idea is to make the Heisenberg uncertainty principle just a little more certain. That's my joke. And part three, I'll introduce one last slide, and that's where if I come back in the spring, it's going to be connecting the real imaginary EEGs with DNA. How to excite the proteins inside DNA chips. Okay, so let's do that. All right. So the historical path to convolution bidirectional neural networks. Back in 1890, William James came up with neurons. Okay, keep on going down. You got the 40s, the 50s. Minsky and Popper, hey, we need at least one hidden layer for it to be meaningful. Well, the guy named Werebos, I don't know how many people really know this, but Paul Werebos invented a first working neural network by nothing more than backpropagation, looking for the minimum of a parabola. That's what we teach in college and in high school. That's all he did. The backpropagation is just minimizing. Just get to the bottom of the parabola in many dimensions. So then convolutional neural network, where they were starting to bring in images, that's Fukushima, and then that's right. Sebenko and Hornet, they actually said, hey, at some point you should be able to do the universal approximation theorem. Means you got a bunch of layers. Why can't I make one single layer out of it? And that's what I'm going to show you. My technique does that. Okay. Now LeCun in '95, he came up with a convolutional neural network with images. He's one of the, and I'm going to show you the first thing was the MNIST data set. And I used to not like the MNIST data set. I mean, okay, it's an example, but the more I play with it, the more I just presented this at a college not too long ago, and it just reveals how these things can work inside the neural network using the MNIST data set. So bidirectional, Costco with Grossberg, they did a bidirectional associative matrix. What I did, they had a stability issue. I stabilized it using the ICA approach that I mentioned in the first slide. So it's just playing with matrices. Okay. And you had, David Lowe. And these things went away until, Krzyzewski and Setgar and Hinton, they came up with a GPU. And that's what brought back image processing, um, convolutional neural networks. It wasn't, I mean, this guy was running it for a while. SIFT. It's a good pattern recognition tool. But when the GPU got back, they took LaCoon stuff, put it on a GPU, and bam, and that's where it goes. So this is a bunch of samples of the MNIST data set. Now the numbers are 0 through 9. If you had to label these, how would you label these? I mean, I could see maybe, is this a 7? Is this a 4? Well, look at this right here. This next one, because I just did this. What numbers do you see? And most people say, hey, I see a bunch of 4s, I see a bunch of 9s. Okay? Guess what? They're all 4s. They're all labeled 4s in the MNIST data set. I mean, I didn't make that up. So what I did recently, I said, well, okay, I had like an 88% accuracy rate, so I went to the 12% of failures and easily found these. So I'm going to show you the scores in a second. Okay, so what do we do? You take an image like you got 9 classes of dogs, whatever. But here's your dog. You put it through the layers. When you do the convolution, you get like the edge to text, stuff like that. Then it keeps on going, and you get an answer at the end. Okay, fine. So you go input matrices, feature maps, and flattened vectors. People don't, I've never seen really study the inside of these feature mapping operations. This is the black box. That's what people call this part, the black box. I do not, and that's the point of the first part of the talk. Okay, so let's look at it. These are the 4s, and this green, I got a section out. Here's the green segments. These are the scores for this guy. This is the scores for this guy. Okay. Now look at these. So for 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Everybody's got a score. People are so brainwashed sometimes. Well, 4 just wins. No, obviously you have to take the maximum one or some other tool you say. But look, the score here was 0.57. It's not like it's 0.99% score that it's a 4. No, 0.57. But look at the 9, 0.31. It's close. But okay, so let's go to here's a 4 and another 4. 0.6 versus 0.1. The other ones are very low. It's a 0.13, 0.03. But if you look, the 4s and 9s are actually competitive. Kind of wild. This one right here, this last 4, 1, 2, 3, 4, 1, yeah, is look how close they are to calling this a 9. Now again, I could go back and train more and whatever, overtrain, and until the score got up higher. But that's not the point. The point is these things score 9 different classes. Look at the scores. So here's down here, these are the other 4s, but obviously look at the scores, 0.51. So this is a 9, 0.41. So these are 4s, but they score higher than the 4s as a 9. So 1, 2, this was for number 3. This one didn't score a 4 at all. It's 0.37. And look, it looks like a 7 and an 8. Again, they're just numbers, and that's all they are. And then down here, this last one, this 9 right here, and why I bring this up is it scored as a 9, 0.3142. This one was 3141. Sorry, not big enough. So this 4 got scored as a 9. And so what if I popped off a couple more pixels? That's what I'm going to do one day is pop off some more pixels and just watch how these scores change. It's going to be a 4 after a while. I know it is. Okay, so if I pop off these top 10. Anyway, but the point is, let me just go back again. Ooh, I mean, these are labeled. So that is a problem with the labeling. That's why it's so difficult. Okay. All right. So let's go on again. So I'm going to show you how I do the convert everything to an association and how you can observe everything. So here's a 2. It goes to the the Gabor filters, blah, 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 all different edge attacks. There's the operations. What I'm going to show you is when they put an input in and go through the operations and do get an output, I'm going to take the input and the output and make an association matrix out of it, skipping the internals. Okay, that's where we're going to go. So this is how I do it. Here's a 2, goes through the filters. And again, we're in the middle of the black box here. This number 2 is a 14 by 14 output of a Gabor filter. It's 196 points. So I take this matrix and I stretch it out. I just unravel it, right? And make a time domain signal out of it, in a sense. So there's 196 points. Here's number 2. The next, and I concatenate them. Now, as you're training, you can see each box react differently because you know where the stopping point is for 196, the next 196. So you can look at the matrix, or I'm going to show you why I put this stuff in a time domain signal approach. All right, let's go to the next one. So again, just to review, I take a 2, I get my filters from an output, and I stretch and concatenate them. Now I'm making so I'm looking at a column, and you'll see why I make the column up. So again, I just want to say one more time, just a refresh again. Here's the 2s. Here's the next layer. This was 16 5x5s this time, and that's 25 times 16, and it loads up those points. So I do it for each layer. Okay, so again, I store this layer right here, layer 1, store it. I continue the neural network process, the normal one everybody sees, more filters. This is the inside stuff, but then I'll stretch that one out too. And this is why I do it. As I stretch them out, I color code them. So this right here, this first column is this, but in color code mode, highs and lows, numbers. That's all. And so here's like 1, 2, 3, 4, 5, 6 outputs across time, I did like 5,000 iterations, training iterations. Yeah, 5,000. And I stick them in a matrix. So I color code them. This is kind of hard to see, but I put them in a matrix form. You're look all the way across. I have 5,000 columns for this one layer of the outputs. So what you're looking at is 5,000 versions of these outputs stretched out and in matrix form. Okay, what are you going to do with that? Well, watch. Here's layer 4. Here's all the number I was putting in, all random order and all that stuff. 5,000 iterations. And do you notice it's kind of smooth in the beginning, then it gets rougher? That's because it's learning. When you first start a neural network, they're all just uniformly, random numbers, and it takes time for them to take on the feature. And so you can see it as you move across, it gets ruddier and ruddier. What I also do is I go across, find all the zeros. Where are the zeros? Where are the zeros? There's going to be 500 of them, 5,000 divided 10 classes. So I got 500. I can see how the zeros are learning left to right. The ones are learning. You pluck them out. And that's in a layer 4. If I go to the output, I'm also capturing the outputs. Here's zeros. You see where it starts in this whole 500 classes. Now these numbers are 1 through 9. But you can see how the number 0 is getting very yellow, very orange. That's because it's doing what it's supposed to be doing. It's learning that when I put a 0 in up here, it is a 0. So you can see it individually learn. So you can see it all together, random inputs. Then you could also section them off and look how they're doing by group number. Okay, well, let's keep on going. So if I do an 8, here's number 8. You unravel that, stretch that out. It's a 28 by 20, 764 points. Here's a layer 1 output. Okay, that's all concatenated Gabor filter. So there's 2, there's 3, there's 4. The matrices are monitoring how they're learning as a matrix method. So I'm not looking at 1, I'm looking at 300, 400 at a time. Okay, so, and the score, it's an 8. Okay, great. Well, here's a really cool thing. Here's the 8. And look up my scores right here. They're 8. So what I'm doing is, if you see the 8, I'm rotating this thing 365 degrees. So I slowly rotate it, It's coming back all the way around 270 degrees, back to 365. This thing is rotated. What you can monitor is, here's the score is the 8. Oh, it goes away. Guess what it becomes? A 3. Keep on rotating it. Guess what it becomes now? 4. And it stays a 4 for a bunch of rotations. Now, I'm rotating these things, I think it's 5 degrees. Oh, no, 1 degree. That's why I had 360. So 1 degree increments. You can see how it's a 4 for a while. But eventually, after I start rotating it back up, it becomes an 8 again. So it's just, you can monitor things. Okay, so I do that. Now, what's really good is, here's a 7. And this is just adversarial stuff. Either you mean it or you don't mean it. But this is the training set. Now, I know I'll show you. Here's a 7. You go through the layers. And what wins? There's the red. It's a 7. Okay, it won. If you slide that 7 over, unless you have another operation that centers it, it's off center, it's not a 7 anymore. It's a 5. 5 wins. So rotating numbers and not setting them up straight or in the center, that affects the output. But you can monitor your layers to see what is it. Because here's the error. Okay, it's a 5 on the output layer, but why can't I look back into the black box and see where did this first mess up? And you know it's messed up in layer 1. You know it did. So you can monitor where these spikes were. So you look at these spikes versus these spikes. You can see here, they're kind of a little actually ratty. Over here, there's spike, spike, spike. So there, you know, it made a difference. All right. Let's go again. So again, I put my numbers in. You got the layers. I stretch them out, make a vector, a long vector out of it. Here's layer 2. Yeah, another long vector out of it. And what can you do with vectors? You can multiply the vectors and form matrices. So if I multiply this layer 1 vector from say a number 7 came in. So this is an output from number 7 layer 1. Well, this is an output from a layer 2. I could take the outer product and form a matrix. So that's what I want to show you over here. So here's an input and I got my output. You can go through all these steps, and that's how you train. I do need to train with it. But after I'm done training, I feel good that, hey, no matter what, there's got to be some association between the input and output. I simply take the input, one of the outputs, organize it, and form a matrix. That's what I do. And I don't have to do these anymore. Okay? So that's what I do. And, all right. That's the advantage of looking at these things as in terms of vectors, not matrices. Okay. So that's what I'm doing. Just about done with this part. So here's the images. They run through. Here's the layers. I collect the vectors one at a time. I make outer products out of them, form a matrix. Now, and I have to, if you look at my patent, I have a patent here. I stabilize it using, again, the single value decomposition from the independent component analysis approach. I actually take the single value decomposition, keep the vectors. Don't forget their amplitude. The norm is 1 of each of the vectors. I throw out the singular values. I don't care how loud a 7 is compared to a 3. I don't care. I just want a 7 and 3 structure. So I throw out the amplitudes of singular values. And that's what stabilized the approach. And several times I've done it. Okay, so there, by the way, so I get a matrix between these 2 layers, another matrix between these 2 layers, boom, 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 and they're all matrices. So this is A by B, because B is the output there, but now B is the input to the next layer. So that's then output C. Well, then the output C is now the input to the next layer, right? That's how you're mapping along. And these are matrices. So guess what? A times B times B times C. In the end, I don't know how this covered up. It's A by F. I can combine the inter matrices. Simple as that, because I multiply them together. And that's how I have an approximation. That's the universal approximation theorem. So I can take layers, make estimates. They're pretty good. They're not as good as the normal thing, but they're not bad. Because you're not going to detail anymore using associations. But in the end, I can multiply the matrices together and get one matrix. It's an A by F. So input right to output. Kind of wild, but you got to multiply these together. All right. So that's again, that's what I'm trying to do. So the CNN, it's processes each step. Here's your process. For each layer is a bunch of these processes. Here, it's just one matrix in between it, the next matrix, and that's how I do it. And there's a patent number. You can look it up and so you want to see what more about it. And so here's my example I was telling you before. So what if I had the right eye, left eye? Say I, couldn't see out of my left eye, but everything else is ready to work. Now here's my right eye, which does work, but I can't transmit out. So what I do is I built a bridge, and I've done this, I tested it works. I can build an association, not between just these layers, but between these layers as well. So it's quadridirectional association. So this right eye can come down. At some point, I come over to a bridge over here because he can't see, I can't put out, but he can work the rest of the way. He can transmit, and boom. So I'm using a different neural network to classify what I'm seeing with this network, and it works, and it should. All right. All right, let's go to part two. Do I take a minute now and anyone want to go back? Or you want to wait? Helen?
Do anyone have questions for the
You can-
part one?
yeah, we'll keep going. Okay.
Maybe a question in part one. So why 7 become 5 in one of the layers?
Oh yeah, because they're just numbers. Because the reason is that's the point. If it's centered, you go through your layers. Well, don't forget, you're convolving with these Gabor filters up here. So that 2 is centered. The Gabor filters are always centered. So if I off-center that 2 or the 7, when it goes through here, they're just different numbers. That's all there is. They're just numbers. That's it. So people gotta, and then that's what I'm saying. So if I took this 7 and slowly and just looked at the output, started slowly, you're twisting it around or moving it left and right, you're gonna see changes here because it's going through the Gabor filters in a different way. Gabor filters are always centered. But if you have an off-centered 4, a 7, look, you're going to get a number. Yeah, does it look like a 5? Well, if you think about it, maybe the 5 part of it when it was trained, shoot, maybe some of this is in there. That's all. There's not much more to it. People think these neural networks, and I've done them. I've done the 200 layer neural networks. It's all the same. They're crunching numbers. Okay. All right. Does that answer? I mean,
Sure. So there's an error. If 7 is recognized as 5, then there's an error there.
yeah. I mean, look at back at the 8s. Here, they thought this was a 6 right here. For about so from angles 220 is like the 200 and or 40. Because look, I think I have 1, 2, 3, 4, 5. Every 5 degrees I'm showing, but I did one for every single degree rotating. So there's an example. Just rotate your 8, and it becomes an 8, then a 3, then a 4, then a 9. It's crazy, but they're just numbers. That's it. Okay. As crazy as that sounds, they're just numbers. So I think it's great for grocery shopping. You can go and take your phone and you can scan it on that box of cereal and you'll see where your phone boxes that in. It's centering it for you. If you for a few years ago you couldn't have been you would have had a problem. Now they box it for you, so that helps you. So think about that. It's just on the box, let alone rotate. Okay. So that's that. And let's get to the this one. So this is called, now we're doing the real. I'll show you what I do in the electroencephalogram. Again, real and now image. So now we're doing the real part. So this is an event-related potential. This is a model mech out of Duke University he used. I looked his paper up. So here come the waves, and hey, this is what it is. Okay. So, yes, I don't timestamp. Then this thing, FFT smear, I'm going to show you some things in a second. So here's I do a single period. This is an EEG in the black right here. it's small because I want to show you the waveforms. And I'll show you, I got an example in a second. This is EEG. What I do is I take a 1 hertz wave, then a 2 hertz wave, just one cycle, then a 3 hertz, 4 hertz, right around 1 point. Then I move the point over and put all these waveforms on it. What I'm doing is, instead of a Fourier transform, because it smears, I'll show you the problems with it. It smears. I'm looking for this striatal beat frequency, and I model it as a sine wave, and it works. I'm going to show you. I'm going to show you. So I do a lot of FFTs. I used to. I hardly even do them anymore. I get very precision oriented. That's the technician back in me again. So let me show you. I'm going after post-traumatic stress disorder and but the epilepsy. I'll show you the epilepsy example I have. I've done that. So again, this is one period of a 10 hertz wave. Okay, and it's a 10 hertz. Great. What people don't realize is if I put a 10 hertz wave and then delay the next 10 hertz wave, this is not a sinusoid. This is a sinusoid because it's one cycle. This is not a sinusoid because it's separated. Look at the Fourier transform. Not only does it does see the 10 hertz, but it sees a 5 and 15 hertz too. Because that's the spreading that occurs when you don't have a consistent waveform. It's simple. It's just simple as that. Nothing really that technical. So I'll show you this, I think, in a second. But yeah, and if you added, it's just, I mean, who would have thought that you had a 5, 10, and 15 hertz wave? If you show them the spectrum part, they said, no, I just have two 10 hertz separating time. So that's the signal processing. I would say, I don't think a lot of developers don't do it. They'll push the button for the FFT. So what I do is I try to work with the developers. I'll set up the algorithm, make the signal processing correct, then hand it to them and make sure they, put it in right. But they don't do Fourier transform, so you got to help each other in the end. All right, so here's the montage I was able to use. G-Tech out of Albany, New York. I had to drive up, and he let me use his machine. Really nice. Okay, so here's the movie. This is okay. So you see, I have a 1 hertz wave. See the 1 hertz? Here's the second row, 2 hertz. This is the same EEG, each row. And by the way, I have 1,000 rows of these behind the scenes, 1 through 1,000 hertz. So it gets smaller and smaller. Now I do one single cycle, but at the same point, then I slide it across. So watch what happens. So every time I slide, I'm doing a correlation coefficient. This is not a wavelet. Wavelets don't do correlation coefficients. They just slide. They don't do the normalization. I do. That's the difference there. So just to show you again. So I fill up this matrix of correlation coefficients. So right down here, I know what the correlations are. Obviously good ones and bad ones, obviously. But do you really pick anything up and watch? Oh, okay. Let me just go to the next slide. Okay. So here is the Temple data set. Yep. The red part are the epileptic seizures, by the way. Okay. So in this one, here's the FFT. You see how smeary it is? It is very smeary because it's taking groups and it smears it in the windows and all that stuff. Okay. Here, the wavelet didn't even see this. Simple as that. Now, did it see it here? Yes, it did. Now, the FFT did see it, but what I want you to see down here, this is my SPSF approach. You see how I have line segments? That's the detail. So at 14 hertz, you see, at 14 and 20 hertz, I can see something very regimented. Then, watch the detail I go to now. I'm spreading this out. Again, here's an EEG, okay? And I read it like an ECT, like, the doctors read off the heart rate stuff. So I look at it that way. So here's the EEG across. This is the labeled frame for this actual seizure. Look what I do with my approach. I'm looking at 1 hertz, then 5 hertz, 6, 7, 8, 9, 10, 11, 25 hertz. And again, I'm scanning. Let me just do this again. I'm scanning it. This waveform I'm going to show you, 1 point at a time. Does it take time? Yes. Obviously, it takes more time than a group FFT. But if you know what you're looking for, you're good because you can see the detail. Do you see how I have these bumps right here? at 2 hertz. Do you see how they go away here? And then they come back. So I got with the clinician. I mean, I knew something was going on with EEG, and I'll get that in a second. What she's saying is this is the aura. So I'm about 30 milliseconds ahead of the epileptic seizure, I can see the aura, and it's running at 2 hertz, and it goes away. And when you're into the seizure, it goes away, and when you're coming out of the seizure, it comes back, and then it just goes back to normal. Here's your 7 hertz. Yeah, look at this one. Here's 15 hertz. It's kind of ratty, bop, 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 bop. Nothing, doesn't really see the aura like the 2 hertz does. But when it hits the beginning of this, look at the pattern. It's like it resonates at 15 hertz. Those are up and down spikes. So there's a 15 hertz coming out of this person, which you can see there's some kind of a frequency thing there. It sees it. It tells you what frequency. So again, patient specific, I would keep my eye on 2 and 15 hertz. Maybe someone else, it might be 2 and 21 hertz. Who knows? But that's what you're going to adapt it to the patient. So it is kind of neat though. It's kind of ratty. It gets boom, very, very resonant, and then it goes back to normal again. Okay, that's just kind of cool. So the big thing here, the takeaway here is at 2 hertz, you can see the aura happen here and coming out of it there. All right, so and I did some stuff that didn't work out good. I've had cow sounds, so I was looking at cows, listening to cows, and recording my EEG up in that spot in Albany. And I presented that once. I had some really cool result, but no, I gotta go back to it. But anyway, that's what I'm looking at. The artificial real, hooking up the brain waves, like operators looking at something on screen, right? Could be a car driving around or watch out for a cow or something. So you have cameras in the car, and you have the brain driving the car. Can they work together as a group assured system? And it doesn't have to be cows, right? You can be a lot of other things. And I think, so yeah, this is back to my last slide. Yeah, my last slide here is I'm bridging it. So I got the artificial, the imaginary part, the neural networks with the 7s and 2s and cows. But here's the brain waves, okay? So I can join those together, make an association between them with these wave with these wave outputs, and there, what I'm doing right now is looking. And this is a book I found by John Butler, DNA Forensics. If you see this red thing coming across, I framed. I think it was like 2 million nucleotides that were part of the part of the COVID strand. And if you frame it, you can find patterns. And this thing is framed, I think it's 786 nucleotides. You can see a repetition. Comes down by column. So again, I took 1 million uh, nucleotides and took 700 at a time and put them in a column because I had a clue how big to frame them. And you can see that there is a pattern here. So there's no pattern here because we're early on this set of nucleotides. And then it comes in strong, then it goes away again. So that's where I'm at. If I come back in the spring, this is what I'm trying to do right now, to tie this to the brains to the artificial. And that is what I got. Yep. And I like that talk from last week too, by the way. I had a few questions I forgot, dang it. But that was really cool. Yeah. So you can see the patterns up here. I like that talk. It was a couple weeks ago. It was good. All right. Any questions now?
I put one in the chat.
Okay. What do you got there?
So,
Yeah, my mind is trying to grab how dogs can detect onset of an epileptic fit. Are there some parallels between what you're showing and how a dog detects the
How a
onset
doctor?
of a fit?
Doctors don't detect it. No, the clinician.
no, not
No,
doctor,
dog.
dog.
Oh, dog.
Dog can detect the onset of
Yes.
an epileptic
Yeah,
fit.
they got to
And
be
this
hearing
seems
something.
very
Yeah.
similar. Yeah.
Yes. Exactly. I think the animals are smarter than human beings. It's just up to us to figure out the freaking animals. Oh yeah, they have
I
banana.
like that.
Yep, the banana spider. When you look at the banana spider web, and I did the frequency analysis, two-dimensional analysis on the web. They have they have a medium pass filter. They have a low block and a high block. I did the Fourier transforms on them, but I knew how to do it. Okay, what the point is, I'm guessing they don't want the wind to clue them in that some bug hit their web. That's low, and they don't want some high screeching passerby to clue. They have it's between something like 30 and 50 hertz. They know there's a kill. That's when they move into the web. So Binary Spider, for instance. Yeah. So no, right, the dog, yeah, the dogs can hear it. I mean, well, I grew up on a farm. The cows lay down 15 minutes before it rains. So I like that. Thank you for bringing that up because I think so it's there. So the dog's there. So I'm not making this up. And then that clinician said, James, let me look at it. She goes, and you really can't see any pattern up here, but you can see it when you do one frequency at a time. And that, again, just a point. That's why I do it. And I do 1,000 of these, 1,000 of these at one time. So at the beginning, it used to take like an hour to do like a 5-minute clip of EEG, but now I got it down faster than that. But the point is, I want to show the existence, and I don't need to do 1,000 different frequencies all the time, right? If I'm looking for EEG, it looks like maybe the first 20 hertz is about all you need. Individuals, yeah. That answer your question there, Shani? Good.
Yeah, it does. I mean, your analogy with the spider is actually spot on.
Yep.
Because
Yeah.
I've actually observed spiders, and they don't react to any wind movements or anything like that. Not even a leaf hitting it. It's when an insect, when an insect hits a web, it's not just the initial impact; it's the struggling as well, and that's the thing that will alert the spider.
That alerts the spider. And so if you take a picture of the web and then just take a cross section, a vertical cross section, the webbing, it's not uniformly spaced. It's not like it's 1 inch, then the next web, and then one. No, it's non-unit. It's like a linear recursive sequence. It's purposely, it's purposely spaced right. I mean,
right. The world of nature has a lot to teach us about how some of these things work. It's not just mathematics. Yeah.
No, right. So you can see I'm detail guy and a technician, and that's why I break everything down to this insanity. But the doctors right now, they're just all they ever look at is right here, the FFT, if they look at that much, the algorithms. I'm like, well, but this is 1960s technology. I mean, yeah, so Cooley and Tukey, they were in there, on the airport, and they came up the fast Fourier transform because they just realized that, you take the transpose of the real, you get the negative part, the phase part. Anyway, what's changed in the 1960s besides GPUs? Why can't we take advantage of the fast computers instead of doing groups of Fourier transform? Take 1,000 points at a time. What's your FFT? Fill it in. Why not just, go one at a time? Because that's the best form of that's the best form of FAT. Well, let me see if I get it out of this pencil. Oh, okay. It's because it's not. It's a striatal beat frequency. I thought it was smart what they came up with. All right, how do I get out of this? Helen, help me. Oh, shoot. Oh, let me go next slide. Uh-oh. Okay. Oh, I know. Excellent. Okay, so that's what I do. Why not take your time? If you're saying there's a striatal beat frequency, then let's look at it for one at a time instead of taking blocks and look at 100 of them simultaneously. No, individually. So that's what I do. All right, and then again, I'm after the DNA next because it's not the protein, right? It's outside the protein is what starts the process of bringing nucleotides down to the outside the cell and into the protein world. So anyway, that's what I'm looking at. Okay. Thank you for the comments. Appreciate that.
I got some more query. Can you hear me?
Yeah, go ahead.
Yeah. First, that initial part of your presentation, you talk about those numbers. I just wonder how you do these identifications of the numbers there, 0 to 9. Do you do some kind of cross correlation for each number? You correlate with all other numbers, and then
yes. I do a cross correlation. So where is this thing here? Where's this line? Right. Okay. See, when I train, I do it for each layer. After the end, do you see how the zeros are finally trained? I had to take the 500, pull them down here in this column. So I take these last few here, the last few ones, and what I'm doing layer by layer is I'll take a good zero. Okay. Just a second here. Just a second. Two. Okay. Yeah. Okay. So here's a 2. Okay. I take the 2 that comes out here. It goes through all those number crunchings, and I get that, but the same 2 comes out here, but just a different form, right? Because it's went through the filters. So I'll take, after this is all trained, after it's all trained, a 2 coming through is going to be a 2. So I'll take a 2 output here, the 2 output here, and I'll do a matrix. Okay, as simple as then I'll put a 3 in. So the outer product is a 2 here and a 2 there. I form a matrix out of that. Then I'll put a 3 in, a 3, put a matrix on that. Yes, then I stack, because I know what numbers they are because I'm in control. Okay, then I stack them together. That's the association technique Costco came up with. So it's an outer product of yeah. So this could have been like one L. It's like an L1. So say the number 2 I passed. I have an L1, one of these, and then it's L2 versions here. So this outer product with this gives me a matrix. I do that for all 10 of them. I go back and do the 2, then the 3, then the 4. Each, so I have 10 matrices. I stack them up, put them all together.
Do you assume that there's some kind of do you assume orthogonality between those numbers?
Oh, no, I can't. Yeah, you're right. Now, again, singular value decomposition does give you that answer. But yeah, I don't know. I can't guarantee that, right? So I don't. But it's good enough, you know?
Yeah, good.
Yeah, that's all.
That's the questions I got. I got 1 or 2 more. The question is when you're looking at the comparison that you made with the FFT method. So, people in engineering, we do use a lot of FFT.
Yeah.
I just wonder if your method could be applied to complex problems in engineering. For instance, vibrations in engineering, whether your method would be more accurate than FFT in determining the frequency content.
No, exactly. I don't even use an FFT where I work right now. It's the last thing I do. I use a caption approach to find the beat patterns. So you'll have a caption, say, well, the caption with the bleats. Oh, I can do that too. I have it on different slides. With the cow, if a cow, it moves, well, I take a caption to find out it's speech processing. So your vibrations you're talking about at speech. Doesn't matter if it's a machine or So I do a capture. I capture the repetition. That's how I frame it. I don't do FFTs anymore. I really don't. Capture them, then frame. That's what I do. So you're exactly yes. Go ahead.
That's brilliant.
Yeah,
that's very good. And the last one, very quickly. I was a bit fascinated when you and the other attendee there were talking about this web, spider web.
Yeah.
I just wonder if the web themselves is not uniform in terms, it's got some kind of variable stiffness.
No,
that,
yes.
That when the spider moves or it sends some vibration, it is a kind of communication between the spider and the web itself in transmitting or kind of elastic waves between the structure, web structure and the spider itself.
No, I mean, absolutely. Yeah, I do a lot of stuff with maximal length, linear recursive sequencing, and the spacing in between them and all that. And it's the same thing. So that's what there was a Sunil, I think, said it. That's what he was talking about. Yeah, no, it's the freaking banana spider knows what the heck it's doing.
That's brilliant. That might be similar to the bees, the honeycombs of the bees.
I got the bees done too. So what's really cool is you get. I had it in the backyard, so I have it. I can't pull it up right now. I don't know where it is, but so I have a bee. I'm recording the bee near the beehive. So I got the bee. He gets clear, and I did a capture. He's actually flying at 236 points of sound, but he repeats. The buzz is very, very periodic, by the way. Every 236 points, it's the same buzz. Anyway, when he get 236 points, when he got to the honeycomb itself,
Yeah.
it went to 254.
Oh, that's beautiful.
Is
That's
that cool?
beautiful.
I
Yeah.
mean, it was clear as day. We're not talking smeary. No.
Yeah.
The thing was, I got it. I can actually present some of those
Yeah.
things. I can do the animals next time, maybe, Helen.
Yeah. Yeah.
I done,
Thanks. Yeah. Thanks
I
so
did,
much. That's
okay.
beautiful. Yeah.
Yeah, I did air conditioners too. Air conditioners kind of cool. You can dive in. There's a 60 hertz pattern in there, right? Yeah. All right. Well, thank you. Thank you. Anything else? You just go ahead and email me, and please CC Helen Ma. Thank you, Helen Ma. She's the bomb.
So
Okay.
maybe,
I have a question. Yeah. Go ahead,
I was-
Sunil. Yes.
yeah, I was going to say that AC comment was kind of interesting because if you could predict an AC about to die a few days before it actually does so,
I never thought
there's
that.
a lot of money to be made there.
You know that? Yeah, I never thought about that. Good. Yeah. No, because again, you just got to do it right, but you can't do it with a Fourier transform. You got to find that beat pattern, and then you go down to that beat pattern, which is 60 hertz. Yeah, it's
Yeah,
there.
put a microphone next to your AC, the outer
Yeah,
unit,
and just
and the
leave
inner
it there.
unit, and
Yeah,
yeah.
yeah. My brother Joe, he's a technician at Kodak. He's retired now. He's got 3 patents. We just beat things down to death. That's what we do. Simple as that. He saved coloring on the film by like 0.3%, which added up to be like $10 million a year. That's what we do. So
That's what I used to do, technician on Kodak Arri 9s or whatever they were called.
is that right?
Yeah, I did that. That was a summer job. Yeah.
Oh, nice. Good.
I have a question for the left eye and right eye test. You just
Yeah.
pick one patient, or you pick a bigger group of patients?
No. This was no patient was right. These are 2 artificial neural networks. I just wanted to show the people, again, yes, I can do bidirectional associations per neural network, but when you learn your matrices, back to your questions, I can tie that matrix there to a slightly different matrix. They're both trained similarly. They're both convolutional neural networks, but I can build this arrow means I have a matrix it's intra-layer matrix for layers 3 and 3. So all I did was an example is I said, so I formed 2 neural networks. I trained them. They had pretty good training. I said, well, let me see if I can do an association between them. And that's what I did. And boy, it worked. But it makes sense that it should. So, and I could do that right eye, and I want to do it next, and I haven't time, sound. So again, I want to hear that cow, see that cow, make artificial neural network to do the speech processing neural network for the cow moo, and then a vision thing. See if I can tie those together in between. Because why wait to the end for the answer? Why wait to the end? Why can't I, start getting the answer back here? What, that's just me. So that was just an experiment I did, artificial neural networks. I came down here, built the bridge, and then I said, okay, from this information here, I don't have anything coming in. So I take this information, come over here, and I go pop, 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 and it worked because these 2 were associated. It's not like I could just take the output, put it in here, and expect it. No, this is a matrix I built between these 2 matrices to bridge them. Yeah.
So what are the virtual left eye and right eye? Are they signals or?
Yeah. I mean, maybe you had 2 cameras. Maybe they're flying around these cameras, and the one can't see, but it still can process. This guy can see, but he's being maybe jammed. Something's in his lens, so he can't send it out. Hey, can I borrow you for a second? Yeah. So he does the right eye. His neural network system is not the same as the left eye. Now it's not the same, but if you bridge a gap, you can send it. You could build something from here and come on down here. Bridge 3 to layer 5. Yeah.
Can this
So
be
it's just
done in,
a proof of concept. Yeah.
Can this be done in real time?
Oh yeah, when this works, okay, and you got to play with it, it's 30 times faster. Could be, and the reason it's faster. Oh yeah, no. Oh, you have to train now. Okay, you have to train, but once it's trained, no, you're 30 times faster because you're not doing these steps anymore. You're taking an input, it takes this matrix, so you put it in 784, it directly outputs a 2352. Boom. You're not doing these steps anymore. The problem is, can I do 1,000 classes, right? Because you saturate the matrix. So that is an issue. But if you can keep it down to 10 different classes and have it organized and build these matrices, yeah, you skip those steps. It's 30 times faster. Done.
Mm.
Yeah. Yeah.
I'm thinking in terms of like milliseconds versus seconds. 30 seconds to 1 second isn't much. But 30
right.
seconds to
But
1 second is. Yeah.
whatever time it took for this. Oh no, this is all millisecond stuff. Yeah.
Oh, okay.
Yes. Yeah. Yep. That's it's 30 times faster. So if it's got, again, if this thing took its own, whatever, 1/10 of a second, this would be 30 times faster, 1/300th. I had the numbers actually somewhere. It's in their presentation I gave. I have the numbers. I've done them. And it made sense, right? But again, the limitation being how big of a matrix can it handle. Nowadays, you can go up to size 10,000 by 10,000. Okay. So that's what brings up the saturation. You can't do 100 classes using this simple technique. You'd have to build it or break it apart or something, because you are limited with your matrices, matrix size, yeah. But you do all the calibration offline. All the calibration is done offline. But when you're trained and it's set to go, and you have your matrices ready to go, now that's it. Boom. Every step here, they got it 8 steps. Here, no, pop, 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 done. So that's it. Yeah. So yeah. Again, do I lose some detail? I can, but I can play around with that. You can fix it up nice, the way you want it, and then pop. So yeah, it works. Yeah. So that's why I'm going. Yeah, good work with bit streams. Communications traffic on your internet and all that kind of stuff. There's things like that you can do. Yeah. All right. Did I answer your question, Helen? Okay.
Thank you. Yeah, sure.
Okay. All right. Well, thank you, everybody. I can, if you have some follow-up questions on those animals, I can send you a few slides. Happy to share. They're actually on my website. I have an example on my website. But send me an email, or again, CC Helen Ma there, and I'd be happy to. If you want a couple examples of the honeybee, I got the sound, and I got the wasp is wild. The wasp. It doesn't have any kind of rhythm to it. It's there, but you don't see it. I've had maybe 3 people see it. I had to use signal processing and find it myself. So the animals are cool. The animals, yeah, they're wild. So, okay.
So one more question: does it work better with GPU? Like your first time you talk about Hinton's GPU?
Wait, where was this?
On the earlier slides, I noticed you show Jeffrey Hinton. He talked about the CNN with GPU. Will anything works better with better GPU?
Oh yeah, that's what made neural networks come back.
Yeah, deep learning GPU.
They went away in They went away in around 90. Let me see, 95. LaRue came up with it, so he did the mailbox. That's what the MNIST data sets for, mailbox zip codes. And so he did that, but they could do 10 classes. They couldn't do 1,000. It'd take long. It wasn't until 2012 these guys used the GPU. And so they actually have basically 10 parallel neural networks. That's what they did. Smart, right? They just had the GPU first. That's it. Was this Stanford? I think these are Stanford boys. Yep. That's all it was. So they brought this back. So the thing that went away in 1995 was brought back 20, it's a competition. And they won by 30%. The scores were like 70, 75%. Then these guys came with their GPU result was like 95%. Like, oh, we need to get GPUs. So that's all it was. No, that's nothing really improved. No, but they could use 96 Gabor filters instead of 12. That's the trick. Yeah, yeah. Thank you. Yeah, that's pretty cool. But Wearbo started it. He doesn't really get the credit. He's the one who started this whole thing. Yeah. So, but I got to tell you this, while everybody's listening, I went to artificial intelligence, AI, those Compass AIs, whatever, Chat GPT, and I took one of the fours. Okay, I say, hey, what I said, my exact words, what number is this? And the Chat Compass GPT came back and says, oh, that's the letter K. I said, wait a minute. I asked you what numbers. You talk with that thing, right? He goes, no, you didn't. You asked me what letter. It's telling me this. This was about 3 weeks ago. I said, wait a minute. He said, here, okay, let's stop dancing around. Okay, you asked me what number. And thank you. This artificial AI, I don't know about it, but needs to be supervised. All right. Okay, good.
Yeah, I also wonder why the 7 won't be recognized as 1.
Oh, I bet. Okay, so seriously, by the way, what I would
Yes.
do, okay, you see how I did for the fours, right?
Yes.
If I get the 507s, and some of them are, they'll be 85, 90%, they'll be scored. You look at the other 10%, I'm sure some of them are going to be ones. Yeah. In fact, I see. Wait, let me see if I get the score right here. Let's look at that question. Well, look at the answer here. I'm looking way over here. Okay. Do you see on the left where it's centered, the one's low, the seven's high. Over here, look, the one is actually more of a one. Five, I don't know why it picked five. Don't ask me. It did. But the one got bigger, didn't it? So it saw part of one. Now, if I rotate that seven a little bit, so you go through these crazy games, but if I put in my 507s, 10% are not going to be sevens, and I wonder how many are going to be ones. That's your question. I just got to look it up. Yeah, yeah. So that's what I do. I look at the answers, the scores. Yeah, so I don't, yeah, right. I look at the numbers. People don't, I don't know why. I look at all these numbers right here. So that's what I'm tracking, all these outputs. Okay, yeah, okay. In this case, 0, 1, the number 2 or the class 2 one with the 0.7%. Fine. But I look at the other numbers to see how close. Because if I just move this doggy left or right or twist them, how does it affect these numbers? More so, how does it affect the interlayer numbers? Well, I just look here. I mean, that's your output. That's a good place to start. But what is being changed here? And that's where you have to look at the Gabor filters. Where are those? Yeah, see these horizontal, angled, all that. They're looking for the edges, and that's all it is. That's it. So, the GPU allowed 96 versions of these.
So when you're doing this with images like that, you're actually only operating in 2 dimensions. So it'd be interesting to see what happens if you extend this to 3 dimensions, effectively rotating the image, not like in a 2D plane, but in a 3D plane. How would that change all of this?
Well, you know what I did? So what I did, I made a grayscale. See this 2 right here? I grayscaled it left to right. So it was lighter gray on the left, and as it came right, it got darker gray. Then because my idea there, just what you're saying is, what if I tilted the 2 up? It would have some of a shadow. So I just made a 2-dimensional shadow to simulate the shadow. And yeah, it messes it right up. It's on another slide. I've already done it. So yeah, you take that too and color code it. And yeah, again, I made this is blue and red, but I mean they're grayscale when they go in. So what I did is I altered the grayscale again from light gray to dark gray, column by column. I built it up. So this is like a light part of the 2 and it's a dark part of the 2 to simulate that it was like I was holding it up at an angle.
Right, putting a shadow on it, so to speak.
Yeah. So yeah, right. And it wasn't a 2 anymore. No.
We
No.
got to get out of two-dimensional thinking, I guess.
Yeah. It's just funny, isn't it though?
Yep.
So yeah. I mean, the banana spider, he's not a straight web. He's at an angle. I might as well think a little more like you're saying. I like that. Thank you.
Yeah, I have a thought about the 7. If you rotate the Arabic number 7
Yeah.
by 180 degrees, it will become a Chinese 1.
Oh, there you go. There you
Yes.
go.
So there's nothing wrong to say that is a 1 in Chinese.
And there'd be nothing wrong with that, would there?
Yeah.
No. Right. So you better
I would
know the
say
context. You got to know the
that-
context.
Yeah, that
Yes.
applies to a lot of languages, though, right?
Sure.
Yeah.
I mean, look at these numbers. Those numbers are from around the world. Now, if you segment out the United States versus Australia versus, Kuwait, come on, it probably improved their accuracies, right? In China. Yeah. Yeah. So, I mean, look at these. Somebody labeled them. Okay, not me. It's interesting. Very interesting. But full of faults, that's for sure. Yeah. Yeah. So, yeah, so, and that's why in the end, I look at the DNA, because for me to get this pattern right here, right, this pattern on the genome, this is the COVID strand. And if you take another look, you'll see, I found this pattern. It's like framing the honeybee. Doesn't matter. I know the buzz. I found the buzz rate using Capstone. And then, so I know how to frame it. Boom, boom. I need to look more into it, but I just wasn't surprised. There's got to be something that resonates to start up, the method of taking the nucleotides from the DNA and bring it down to the protein, leave the freaking molecule, and start making up there outside the nucleus. So
when looking at some of these images, one thing I do notice, and I ran into this a few times, is that if you're measuring signals and visually displaying them, if the frequency is high enough, you get a lot of aliasing in there, and the image actually kind of lie to you. How do you deal with that?
When someone gave me the problem, I would sit there and figure that out. No, I know exactly the problem you're talking about, but you're gonna have to figure out. You would say, and again, you got to be decent with your filtering. Just don't, I love MATLAB. I own my MATLAB. It's the best program out there, but still, you got to do your own work ahead of time. So how would you deal with that? You analyze the living heck out of it. Yeah. And build your own bridge filter. I did it for ECGs, heart rate analysis. I do 4A. They were doing 4A. I said, no, let me rank this up. And so I built a better filter because I made it more precise. So I knew what filter to apply because I knew the details of what not to put in there with the aliasing. Exactly. Yeah. So depends on the bandwidth and all that. Yeah, go ahead.
Kateri Bolinjo has a question. Have you talked to any geneticists about using this method for their analysis?
I tried to get in, they call it the NIH here in America, and I was in a program, they put me in a program, but funding got cut. I was close to getting this done. Yeah, no. So I'm going to try it again by March. Right. But wait, with the gene codes, they just started. Okay, my heart rate, my EEG, and the artificial, I got that down. Again, 2 patents. The thing here, the genome, is something I've been studying. I've studied for about a year and a half, to the point I'm like, I don't know anything about this stuff. I thought I knew stuff. The more I read about it, the less I know. So no, I'm still a few months away from, I'm going to try and put a patent in by April. So January is my start date. So I haven't really jumped in yet with someone. That's what I'm looking to do next. So, thank you for that question. Yeah.
And Ron has a question. Are there other clinical diagnostic data sets that could be used with this type of analysis other than EEG?
Well, like what? Yeah. Like what? I
He
mean,
puts on the chat, or maybe Ron, can you?
I just EEG because that was available. See, I worked with a guy out of Duke University for a while, And what he was doing was his approach. I could just stare. I said, I could tell you which anodes. I could tell the headset right here. I could tell which ones were hooked up on the left side and right side just from looking at the waveform. He goes, what? So he got his technician to go out, and they came back and said, well, the guy's right. Yeah, he sectioned them off correctly. So he was just doing a thresholded version. So what I did, I went down, got the EEG from Temple University, and then MIT's got a database, and I looked, and that's where I started, raw EEGs. Now, what else could I do at the end? Again, I like the air conditioner idea. I need to put the microphone there. I mean, it applies everywhere. Talk about the signal processing part, the animals and all that. Again, that honeybee who changed his frequency when he entered the door of the honey hive. That's crazy. So those are all sound waves, real ones I've gotten. I've done the cow, the sheep, the bat is wild. I can see the pop of the bat at the end. So I've gone to a lot of different data sets that are available. Yeah. Does that answer the question though, or?
I want to say yes.
Okay, good. Okay.
And Shunil has other question, not a dot, but heart signals.
Okay, go ahead.
Shunil, do you have a question about heart signals?
No, that was more of a comment to the previous thing about EEG, but the heart, you can attach all these monitors to your chest, and they watch your heart under stress and so forth. But is this kind of thing
Exactly.
applicable here?
Yes, that's exactly right. So the EEG, they look at your heart rate. Okay. I look at 300 beats at a time because I frame the heartbeats. I know a heartbeat pattern, right? So I know it's like, if it's 60, it changes, it's fine, but I frame them and see them. And that's why I want to do the EEG frame. I think a doctor should be able to see that. But it's, look, it's their world. They know a few people have seen my stuff, but I present this Society for Neuroscience. And, it's just a game. So, but eventually it's going to get out. Oh, eventually. Gotta get in the club. So that's, yeah.
You mentioned that the processing time, like in milliseconds. I just wonder if it can go further lower, because I was thinking of applications of detecting potential instabilities. Suppose that you got a phenomenon which give us a pre-signal,
Yeah.
and then within a very short period of time, that pre-signal would result in a kind of instability. Whether your method is able to detect very quickly this signal instability, perhaps in less than milliseconds,
Oh,
in
I
order
think
to prevent the instability.
now if you knew the source of the pattern, if it's again a sinusoidal, because vibrations start and then they build up and then boom, right? So no, I think the answer is yes to that. And by the way, again, where's that? Where's my little this thing? I just made the movie of it, but no, this thing's now this right here. There's 1,000 points. And so it's an EEG. So I think it was like you're looking like at 4 seconds right here, by the way. But no, this whole thing be done in, I mean, millisecond, probably less than that. This no, but if you know what frequencies you're worried about starting up, that's what it is. Because this isn't that's instantaneous. That's just a movie. But no, that's instantaneous. I'm telling you, it goes fast. Yeah. Yeah.
Yeah, if that's the case, it's got a tremendous potential applications, particularly because I've got engineering background. I think often in terms of engineering, so I see potential if there are signals that we know the precursor of instability, and if you can detect very quickly that precursor, that we can engineers can develop preventive measure to prevent a major instability. That's very interesting. Thank
Yeah.
you so much.
Yeah, okay, yeah, because right here, look, and it's a clinician that found it. Look, James, that's the aura. Like, really? I mean, I didn't know that. So you have to work with the expert in the field, but But I was looking here at the time. You see how this is blank by? You see like the 5 hertz, it goes blank at 5 hertz, then it comes back to beats. These are the beats. That's kind of wild. No, so and this is very quick. Yeah, and I go back to that bridge that shook to pieces, right? Those was it 4 hertz wait the wind that was the Narrows Bridge or whatever bridge that was, it blew it up, right? Because something sets off the vibration. Yeah, yeah, impulse response. Yeah.
That's very good. Yeah, thank you.
Okay, thank you.
And Ron has a comment. Seems like this kind of analysis will be useful for future quantum-based sensors.
I
that
think that's
potentially
where
can
it's
be
going.
used-
Yeah, yes, because I'm monitoring. Yes. That's what I like this, your quantum club here. That's where this is going to go in the end. That absolutely. Yeah. The snap, you know, different beats, different frequencies, different places. Yeah, no, yeah. Absolutely. So
So for the JPEG, for the previous slide about the JPEG, I saw two patients, one in 2021 and one in 2019. So you just pick two patients to do the experiment, or can you
oh
pick?
no, God, I've done 100 of these patients, a couple
Oh,
hundred.
okay.
Oh yeah, no. I just picked two to show here,
Oh,
yeah,
okay.
because they have their IDs, not their names or anything. But no. This no, I'm happy with the EEG. Very happy with this Striatal Beat Frequency approach. But I call it the stupidest patent I would ever probably write because all I do is a sine wave at a time and move it. But again, you have to unlearn what you're taught in college with the FFT. I mean, if you want a general frequency feeling, sure. No, you got bandwidth. No, but if you want to narrow it down to someone's brainwave, no, you know, you customize it, right? All right. Yeah.
Terry Bollinger asks, do you have any papers covering these slides? I may have already missed it in your slides.
You know what, Helen, I will send you. Yeah. Anyway, the answer is yes. I just presented one. Yeah, SPIE. Look up James LaRue SPIE conferences, and then the Applied Imagery Pattern Recognition Conference. Yeah. I'll give you a list. I'll send a list to Helen.
Sure, but some of them you need to have a membership to log on to view your full paper.
Oh well, I send my paper to you.
Sure, or I
You
can
want a
forward the
couple
paper.
papers? Yeah.
Yeah, that would be great. Thank you. PDF or something, yeah.
Yeah. Okay, fine. I'll send it to
Yeah.
Helen. Just reach out to Helen. I'll send them to her. Okay.
Very cool. Thank you.
All right. You're welcome. I think I stopped sharing. I think I'm off. Am I off? We're done, right?
Yeah, sure. I got a nice comment. Thank you so much for this interesting work.
Guys, ladies and gentlemen, thank you for asking questions. Appreciate it. Really. Thank you. Okay.
Thank you for the great. There'll be a great for XX. Thanks. That's from Terry Bollinger. Yeah.
Okay, good. Thanks. So I'll send a couple of papers. Let me find them. I'll send them to you, Helen. Okay.
Yeah, sure. Just send me everything I can forward to the participants.
Okay. Well, they're papers. Yeah. Okay. Sounds good.
Sunil, do you have question? I saw you unmute.
No, I was just going to say thank you for the presentation. It's a great presentation.
Well, thank you very much.
Right.
All right. Thank
I
you.
would
And
say
how
thank
about-
you also. I would say thank you also. It's very interesting, interesting materials.
It's hard to get across to the people who are established. They don't want to, so you know how it is. I mean, I've listened to two of yours guys, the way you guys present, and you're open-minded. That's nice. It's few and far between. So thank you.
And Ron say love the papers.
And what now? The what?
Ron just comment love the papers.
Oh, okay. Thank you. Okay.
Yeah. Just send me the list of your paper.
Yeah, I
and
got about
PDF.
three,
Yeah.
four of them. I got 3, 4 of them. I'll send them to you. Sounds good.
Sure. And
right.
you're welcome to come back to give a new talk next year.
Okay.
Yeah.
All right. Sounds good. Thank you very much.
So thank you again for everybody coming, and the recording will be available soon.
Okay. Thank you.
Thank you for your time. Thank you.
Hey, guys. Thank you all. Bye. Okay, let's see how I get out of Miss Helen. Oh, here you go.